Welcome to the deep dive. This is where we take some really fascinating information, pull out the key bits, the important stuff, and basically give you a shortcut to being properly informed. And today we are setting off on, honestly, an awe-inspiring journey. We're looking at cosmic wonders, unraveling the universe's deepest mysteries.
A big one.
It really is. I mean, for literally thousands of years, people have looked up at the sky. And you're captivated, right? Not just by how beautiful it is, but by these huge, existential questions it brings up.
Absolutely.
So, okay, let's unpack this. Let's explore some of the most mind-bending cosmic enigmas out there. We're going to be using insights from this great source material, a Cosmic Wonders video script, to sort of cut through the noise.
Yeah, get to the heart of it.
Exactly, to really grasp what matters about these deep secrets of the cosmos.
And that's exactly what we're aiming for, to sort of guide you through all these layers of cosmic mystery. What's really fascinating here, I think, is how just looking at the stars has changed. From ancient myths and stories to, cutting-edge science today. But the basic questions, they're still the same.
Right, where did we come from?
Exactly.
Yeah.
Where do we come from? What's everything made of? And, where do we fit in?
Yeah.
And scientific progress keeps pushing what we understand, giving us incredible answers. But maybe even more remarkably, it keeps showing us completely new mysteries, new layers.
That's so true.
So today, we'll be navigating through the universe's fiery start, that enigmatic dark matter shaping galaxies, the pull of black holes, and even that really mind-bending idea of the multiverse.
Wow. Okay.
Yeah, get ready for some real aha moments, and maybe some surprising facts that might just challenge how you see reality itself.
Okay, so let's kick things off right at the very beginning. The absolute genesis event, the Big Bang.
The start of it all.
Right. Cosmologists figure this happened about, 13.8 billion years ago?
I remember, yeah.
And the picture they paint is this incredible explosion from something called a singularity, which sounds intense, like an unimaginably dense, infinitely hot point. And it quite literally gave birth to time, space, and all matter.
It really did.
When you really stop and think about that, I mean, every single atom in your body, every star, every galaxy stretching out for billions of light years, it all came from that tiny, tiny point. It's a concept that just reshapes how you think about existing, really.
The implications are just monumental, exactly like you said. A single origin for everything we see.
Yeah.
And the Big Bang Theory, it's not just some, philosophical musing.
Right, it's science.
It's the bedrock framework for modern cosmology.
Yep.
And it's supported by so much observational evidence. It describes how, from that initial unbelievably hot, dense state, the universe just started expanding and cooling down.
Okay.
And that cooling allowed the first particles, like quarks and electrons, to form, and protons and neutrons.
The building blocks.
The very basic building blocks, which then combined into the first simple atoms, mostly hydrogen and helium. And then, over huge amounts of time, gravity started sculpting those simple atoms into, everything we see now. Stars, galaxies, the whole cosmic web structure.
But it wasn't always straightforward, right? The basic Big Bang model had some issues.
It did, yeah. For decades, there were some significant challenges.
Yeah.
Things that struggled to explain easily, particularly about certain uniformities and structures we see.
Like what?
Well, for instance, why are parts of the universe that are incredibly far apart, so far apart, that light shouldn't have had time to travel between them since the Big Bang? Why are they at almost exactly the same temperature? That's called the horizon problem.
Okay. How could they know about each other to even out their temperature?
Exactly. It seems like they shouldn't have been able to communicate, thermodynamically speaking. And then there's the flatness problem. Why did the universe on the largest scales appear so incredibly flat?
Flat, meaning?
Meaning its geometry is very close to standard Euclidean geometry, like a flat sheet of paper, not curved like the surface of a sphere or a saddle.
Got it.
The standard Big Bang model on its own didn't have a really compelling explanation for why it would be so flat. It also implied a kind of suspicious fine-tuning or coincidence in the early universe.
And that phrase gave birth to time, space, and all matter. It really pushes our intuition, doesn't it?
It absolutely does.
Does it mean that before that moment, time and space just didn't exist as concepts?
That's the implication.
Yeah.
As hard as it is to grasp.
Yeah, it's almost impossible for us to truly picture an infinitely dense point holding the entire future cosmos.
Yeah.
Think about it. A moment before time itself existed, where space hadn't even started stretching out.
Mhm.
You have to sort of shed your everyday understanding of how things work. It's totally alien to our experience.
It is.
And this whole idea, this radical concept of a dynamic universe, one that evolves and has a definite beginning, it's so different from older ideas, right? Where the universe was just static, always there.
Exactly. Those static models prevailed for a long time. The Big Bang gives the universe a birth certificate, you could say, a starting point for everything.
A cosmic birth certificate. I like that.
And the very idea of a birth means those initial conditions were absolutely critical. They fundamentally dictated everything that came after.
How so?
Well, the initial energy density, the precise rate of that initial expansion, the tiny quantum variations present right at the start. These were like the cosmic blueprints.
Okay.
They ultimately led to how galaxies formed, how stars were born, and eventually how complex chemistry and even life could emerge. The challenge is connecting that initial, almost incomprehensible state to the complex, structured universe we live in now.
Right.
But, this initial explosion, as dramatic as it was really just the start of the story. Something even more dramatic and way faster happened almost immediately after.
Ah, okay. So the Big Bang happens, but then there's an Act 2 almost instantly.
You could say that. A very, very fast Act 2.
Okay, so we have this incredible origin, the Big Bang. But like you said, the story gets even more wild right away. Because in those first fleeting moments, the universe underwent an incredibly rapid expansion, a phenomenon known as cosmic inflation.
That's the one. Inflation.
And here's where it gets really interesting, you said. This wasn't just gradual expansion.
Not at all.
It was exponential growth. Faster than light speed for space itself.
For space itself, yes. Not for objects moving through space, but space itself expanding faster than light. It blew the universe up from something maybe subatomic to maybe the size of a grapefruit or even much larger in this ridiculously tiny fraction of a second.
Like less than a trillionth of a second.
Something utterly minuscule like that, yeah. An incomprehensible burst of expansion.
Okay, my mind is slightly bent already. Why did that happen? Or why do scientists think it happened?
Aye, good question. So cosmic inflation theory was proposed specifically to solve those puzzles we just talked about. The horizon problem and the flatness problem.
Ah, okay. It ties back to those.
Exactly. Elegantly solves them. For the horizon problem, how distant regions have the same temperature, inflation says, well, before inflation blew everything up, those regions were actually very close together.
Oh, okay.
They were in causal contact within a tiny pre-inflationary patch. They had time to even out their temperature. Then, whoosh, inflation stretched that tiny uniform patch to enormous scales.
Like stretching a small, smooth piece of rubber really, really big.
Precisely. Making it appear uniform across vast distances. It's like a cosmic smoothing iron.
Okay, I get that. And the flatness.
Same idea. If the early universe had any initial curvature, like being slightly spherical or saddle-shaped, inflation would have stretched it out so much that, from our perspective within it, it now looks almost perfectly flat.
Like blowing up a tiny crumpled balloon.
Exactly the analogy. You blow it up enormously, and any small patch on the surface looks flat to an ant living on it. Inflation does that for the universe's geometry. That's how it explains the universe's large-scale uniformity.
That's incredibly neat, actually. But inflation does more than just solve problems, right? It explains where structures came from.
It does, and this is maybe the most profound part. It explains the origin of all the large-scale structures, galaxies, clusters, superclusters.
How? From that super smooth state?
Well, it wasn't perfectly smooth. Inflation theory posits that tiny ripples, basically quantum fluctuations, were present in that initial state.
Quantum fluctuation,
Right.
like an empty space.
Exactly. Even empty space at the quantum level isn't truly empty. It's this sort of seething foam of energy fluctuations, virtual particles popping in and out of existence constantly.
Okay.
Inflation took these microscopic quantum jitters, these tiny variations in energy density that are normally confined to incredibly small scales, and stretched them, blew them up to cosmic proportions. It literally froze them into the fabric of expanding space-time.
So tiny quantum weirdness became the blueprint for galaxies.
That's the idea. These slightly denser regions became the seeds, where gravity could later pull matter together to form the first stars and galaxies. The slightly less dense regions became the voids.
Wow. And we can see evidence of this.
We can. These incredibly faint variations are still detectable today. They're imprinted in the cosmic microwave background radiation, the CMB.
The afterglow of the Big Bang.
Precisely, often called the baby picture of the universe. When we map the CMB, we see these tiny temperature differences across the sky, corresponding exactly to those stretched quantum fluctuations predicted by inflation.
That's powerful evidence.
It's incredibly powerful support for the theory. But, while inflation works beautifully in explaining these big picture things, scientists are still searching for definitive answers on the specifics.
Like what? What's still unknown?
Well, for instance, what exactly caused inflation? What was the nature of the energy field, often called the inflaton field, that drove this hyperexpansion? Was it one field? Multiple fields? What were its properties?
Right, the mechanism behind it.
Exactly. We have models, but nailing down the specifics is ongoing work. And finding even more direct evidence would be huge.
What would that look like? More direct than the CMB map.
The holy grail right now is detecting primordial gravitational waves.
Waves in space-time itself, generated during inflation.
That's the idea. Inflation would have been such a violent process, shaking space-time so intensely, it should have produced these gravitational waves. They'd be incredibly faint now, but they would leave a specific signature.
Oh.
They'd leave a particular kind of twisting or curling pattern in the polarization of the CMB light. We call these B modes.
Okay.
Experiments like BICEP, Planck, and upcoming ones like LIGHTBIRD are searching really hard for this B mode signal. Finding it would be almost like seeing a direct snapshot of inflation happening.
That would be incredible. Game-changing.
Absolutely game-changing. It would confirm one of the most, outlandish but powerful ideas in all of science. So we have this amazing origin story, Big Bang plus inflation. But then, as we started looking closer at the universe that resulted, we found it's mostly made of stuff we understand even less well.
Right. So, moving on from the very beginning, let's talk about the stuff that actually shapes the universe today. And first up is this incredibly mysterious substance, dark matter.
The invisible stuff.
Yeah, described as the invisible glue holding galaxies together. And the key thing is, it's invisible because it neither emits nor absorbs light.
Correct. Doesn't interact electromagnetically at all.
So we can't see it with telescopes, radio waves, nothing like that. Yet its presence is felt purely through its gravity.
Purely through its gravitational effects on the stuff we can see.
It's like that iceberg analogy, right? What we see, stars, gas, dust, that's just the tiny tip. Most of the universe's mass is this hidden component.
That's a very good analogy. The visible stuff is maybe 5% of the total mass energy budget of the universe. Dark matter makes up about 27%.
Wow, over a quarter of the universe is this invisible stuff. So how did we even figure out it was there?
Well, if we connect this to the bigger picture, it wasn't just one piece of evidence, but several converging lines that pointed towards it. It came from observations that just didn't make sense with only the visible matter.
Like what?
The earliest really compelling evidence came from studying how spiral galaxies rotate. Back in the 70s, astronomers like Vera Rubin noticed something odd. Stars way out on the edges of galaxies were orbiting just as fast or even faster than stars closer to the center.
Okay. Why is that odd?
Because based on the gravity from the visible stars and gas we could see, those outer stars should have been moving much slower. Gravity's pull should drop off with distance.
Right, like planets further from the sun move slower.
Exactly. But they weren't slowing down. The only way to explain their speed was if there was a huge amount of unseen mass surrounding the galaxy in a giant halo, providing extra gravity.
Ah, the invisible glue.
That's the idea, holding those outer stars in. Then came evidence from galaxy clusters.
Groups of galaxies.
Yeah, massive clusters. By looking at how light from background galaxies was bent as it passed through the cluster, a phenomenon called gravitational lensing.
Okay.
Scientists could map out the total mass distribution in the cluster. And again, the mass needed to produce the observed lensing was far, far greater than the mass of all the visible galaxies and hot gas combined.
So more missing mass.
Lots more. And also, the way the universe itself is structured on the largest scales, this sort of cosmic web of galaxy clusters and filaments, separated by vast empty voids. And our simulation showed that this structure forms much better and matches observations if there's this underlying scaffolding of cold, dark matter, pulling normal matter together gravitationally.
So multiple lines of evidence all pointing to this invisible mass.
Exactly. Galaxy rotation, cluster dynamics, gravitational lensing, large-scale structure.
Yeah.
It all points to dark matter. But despite all that, its true nature remains one of cosmology's most pressing unsolved problems.
Why is it so hard to figure out what it actually is?
Because it's defined by what it doesn't do. It doesn't interact with light, so we can't see it. and it seems to interact very, very weakly, if at all, with normal matter except through gravity.
So it's like trying to catch a ghost. It just passes right through everything.
Pretty much. That makes detecting it directly incredibly difficult. You need extremely sensitive detectors looking for incredibly rare interactions.
It really is a huge puzzle. So when we talk about its true nature, what are scientists thinking it might be? Like, what are the main candidates? Are they looking for new particles?
Yeah, the leading candidates are definitely new types of elementary particles, things not included in our current standard model of particle physics.
Okay.
For a long time, the front runner was a class of particles called WIMPs.
WIMPs.
Weakly interacting massive particles. The idea was they'd be quite heavy, much heavier than protons, but they'd only interact via gravity and the weak nuclear force, hence weakly interacting.
Making them hard to spot.
Extremely hard. Another popular candidate now are axions. These are hypothesized to be much, much later particles, also interacting very weakly. They were originally proposed to solve a different problem in particle physics, but they also fit the bill for dark matter.
Interesting. So how are they trying to actually find these things? You said it's like catching a ghost.
They're trying several approaches. There are direct detection experiments. These are usually built deep underground.
Why underground?
To shield them from cosmic rays and other background radiation that could mimic a dark matter signal. They typically use large tanks of a target material, like liquid xenon or germanium crystals, and they wait, hoping a dark matter particle sailing through the Earth will occasionally bump into one of the atomic nuclei in the detector, causing a tiny flash of light or vibration that they can detect.
Wow, looking for a tiny needle in a cosmic haystack.
Exactly. Then there's indirect detection. This involves looking for signs of dark matter particles annihilating or decaying out in space.
How would that work?
If dark matter particles collide and annihilate each other, they could produce standard particles like gamma rays, neutrinos, or antimatter, which our space telescopes could then detect as an excess coming from regions where dark matter should be dense, like the center of our galaxy.
Okay.
And finally, particle accelerators like the Large Hadron Collider are trying to create dark matter particles by smashing known particles together at incredibly high energies.
See if they pop out of the collisions.
Basically, yeah. Look for missing energy or momentum in the collision debris that might indicate an invisible particle was produced. So far, though, no definitive detection from any method.
Still searching. And it's just amazing to think, like you said, if dark matter wasn't there, galaxies would just fly apart.
Pretty much. The outer stars would escape, the beautiful spiral structures wouldn't be stable, and the whole cosmic web wouldn't have formed the way it did. It really does seem to form these vast, shadowy halos around galaxies, silently dictating how they form and move. It's the unseen architect, in a way.
Okay, so dark matter is the invisible glue holding things together. But then there's another mysterious component doing the opposite.
That's right. If dark matter provides the gravitational pull, something else is providing a cosmic push.
And what a push that turned out to be. This discovery in the late 90s really shook things up, didn't it?
Oh, absolutely. Paradigm shifting is not an exaggeration.
The finding that the universe's expansion isn't slowing down due to gravity, as everyone expected.
Right. That was the standard assumption for decades.
But instead, it's speeding up, it's accelerating, pushed by this mysterious force we call dark energy.
Exactly. It was completely unexpected. Most cosmologists thought the expansion should be decelerating. Gravity pulls things together, right? So it should be acting like a brake on the expansion.
Yeah, maybe it would expand forever, but slower and slower, or maybe even collapse back eventually in a big crunch.
Those were the main scenarios considered. But then came the surprise.
How did they figure it out? What was the evidence for acceleration?
It came from observing very distant type Ia supernovae.
Okay, supernovae exploding stars. Why type Ia specifically?
Because type Ia supernovae are incredibly useful as standard candles.
Standard candles? Meaning they always have the same brightness.
Essentially, yes. They occur when a white dwarf star in a binary system pulls too much matter from its companion and exceeds a critical mass limit, triggering a runaway thermonuclear explosion. Because this mass limit is pretty consistent, the resulting explosion has a predictable, standard peak luminosity.
So if you know how bright it should be, you can figure out how far away it is by measuring how dim it appears to us.
Precisely. The dimmer it appears, the farther away it is. So, two teams of astronomers were using these supernovae to measure distances to very far away galaxies and map the universe's expansion history over billions of years.
And what did they find?
They found that the most distant supernovae were consistently dimmer and therefore further away than they should have been if the universe's expansion was constant or slowing down.
Dimmer than expected, meaning they'd been pushed further away than predicted.
Exactly. The only way to explain how far away they were, given their redshift, which tells us how much the universe has expanded since the light left them, was if the expansion of space itself has been accelerating over the last few billion years.
Wow. So the universe is stepping on the gas pedal?
In a manner of speaking, yes. This mysterious dark energy started dominating over gravity's pull somewhere around 5 or 6 billion years ago, causing the acceleration.
This raises a huge question then. How can a force push against gravity on cosmic scales? Gravity attracts. What makes dark energy repel?
That's the billion-dollar question, maybe $1 trillion. Its nature is deeply mysterious. Unlike gravity, which is associated with matter and energy, dark energy seems to be a property of space itself.
Like empty space has energy.
That's the leading idea, often called a cosmological constant or vacuum energy. It suggests that even a perfect vacuum isn't truly empty but possesses some intrinsic energy density.
Okay.
And according to general relativity, this vacuum energy would exert a negative pressure, effectively acting like anti-gravity, pushing space apart.
So as the universe expands and makes more space,
you get more of this vacuum energy, maintaining a constant density and driving further acceleration. It doesn't dilute away like matter does.
That's conceptually really difficult. It's not intuitive at all.
Not in the slightest. It's one of the biggest challenges in fundamental physics. Why does empty space have this energy, and why does it have the specific, very small but non-zero value that we observe?
And the scale of this, combined with dark matter, is just mind-blowing. You said earlier dark matter is about 27%. What about dark energy?
Dark energy makes up about 68% of the total mass energy content of the universe.
So wait, dark matter 27%, dark energy 68%? That's 95%.
That's right. Together, dark matter and dark energy make up over 95% of the cosmos, yet we barely understand them.
Less than 5% is everything else. Stars, planets, gas, dust, us.
Everything we can see and interact with directly, yes. All the stuff described by the standard model of particle physics is just a tiny fraction of the cosmic inventory.
That's humbling. It highlights just how much we don't know. We're trying to understand the universe when 95% of it is made of invisible, mysterious stuff.
It's incredibly humbling, and it drives a lot of research, obviously, trying to figure out what these dominant components actually are.
Are there other ideas for dark energy besides the vacuum energy thing?
There are. Another possibility is called quintessence. This proposes that dark energy isn't a constant property of space, but rather a dynamic, evolving energy field that fills the universe.
So it could change over time?
Potentially, yes. Its strength might vary, which could lead to different future scenarios for the universe compared to a constant dark energy. Testing whether dark energy is constant or dynamic is a major goal of current cosmological surveys.
And this all leads to questions about the ultimate fate of everything, right? If it keeps accelerating.
Exactly. The implications are profound. If dark energy remains constant or keeps strengthening, the most likely scenario is often called the Big Freeze, or heat death.
Sounds cheerful.
Not particularly. The universe just keeps expanding faster and faster. Galaxies get pushed further and further apart until they're effectively isolated beyond each other's cosmic horizon. Stars eventually burn out, matter decays, the universe becomes incredibly cold, dark, and empty.
Just fading out.
Fading out into infinite cold darkness over trillions and trillions of years. A less likely, more speculative scenario is the Big Rip.
The Big Rip.
This could happen if dark energy actually gets stronger over time, becoming something called phantom energy. In that case, the accelerating expansion will become so powerful it would eventually overcome the forces holding things together.
Literally rip things apart.
Yes. First it would tear apart galaxy clusters, then galaxies themselves, then solar systems, then planets, and eventually even atoms and nuclei. Literally ripping the fabric of reality apart.
Okay, let's hope it's the Big Freeze then.
Most current data favors the Big Freeze scenario, but yeah, the Big Rip is a theoretical possibility depending on the precise nature of dark energy.
So you have this contrast, the initial Big Bang expansion, then gravity trying to slow things down, and now dark energy taking over and accelerating everything apart.
It's a cosmic tug of war, where dark energy seems to be winning in the long run, dictating the universe's ultimate fate.
Wow, okay. From these enormous scales of expansion and cosmic fate, let's zoom right in now to some of the most extreme objects within the universe. All right, let's get ready for some serious mind-bending because now we're diving into black holes.
The ultimate gravitational monsters.
Yeah, described as regions where gravity is so strong that not even light escapes. It's just an incredible concept.
It really is.
And what's amazing is their existence was predicted by Einstein's equations, his theory of general relativity, way back like over a century ago.
That's right. Carl Schwarzschild found the first exact solution describing a black hole shortly after Einstein published his theory. But it took decades for the idea to be fully accepted and understood.
And now we're actually starting to see them, in a way, or at least see their effects directly, imaging their surroundings and detecting gravitational waves from them colliding.
Exactly. It's a stunning confirmation of theory meeting observation, especially in the last decade or so.
So let's talk about the key feature, the event horizon. What exactly is that? Is it like a surface?
Not a physical surface you could touch. It's better to think of it as an information boundary. A boundary in space-time.
The point of no return.
The point of no return.
Yeah.
Once anything matter, light, information crosses the event horizon, its fate is sealed. It cannot escape the black hole's gravitational pull. It's inevitably drawn towards the center.
Towards the singularity.
Towards the singularity at center, yes, where space-time curvature theoretically becomes infinite.
So what happens if, hypothetically, you were falling into one and crossed the event horizon? What would you see? What would someone watching see?
Okay, two very different perspectives. From an outside observer's point of view, watching you fall in, they would see your clock appearing to slow down as you approach the horizon due to gravitational time dilation. Your image would get redder and dimmer. You'd seem to slow down, taking an infinite amount of time to actually cross the horizon, eventually just fading from view as the light escaping gets stretched too much.
So they never actually see me cross?
Never actually see you cross, but from your perspective, falling in,
Yeah.
you wouldn't notice anything particularly dramatic right at the moment you cross the event horizon. You just continue falling inwards, accelerating towards the singularity.
Okay.
Until the tidal forces become overwhelming. This is called spaghettification.
Spaghettification. Seriously, the gravity at your feet would be so much stronger than the gravity at your head that you'd be stretched vertically and squeezed horizontally, like a piece of spaghetti.
Oh, wow. Not a pleasant end.
Not at all, before being ultimately crushed at the singularity.
Okay, and there are different kinds of black holes, right? Not all the same size.
Correct. We mainly talk about stellar mass black holes and supermassive black holes. Stellar mass are
formed from the collapse of individual, very massive stars at the end of their lives. They typically have masses maybe 3 to a few dozen times the mass of our sun.
And supermassive.
These are the behemoths found at the centers of most large galaxies, including our own Milky Way. Our central black hole, Sagittarius A, is about 4 million times the mass of the sun. Others can be billions of times the sun's mass.
Billions? How do they even form?
That's still an active area of research. It likely involves the merging of smaller black holes and the accretion of vast amounts of gas and stars over cosmic time. But they play a huge role in how galaxies evolve.
Right, they're not just passive objects.
No, their gravity influences the orbits of stars in the galactic center, and the energy released as matter falls into them can regulate star formation throughout the entire galaxy. They're like cosmic anchors and engines.
And the evidence we have now, it's moved beyond just theory. You mentioned imaging them.
Yes. What's truly fascinating here is the recent observational evidence. The Event Horizon Telescope collaboration managed to produce the first direct image of a black hole's shadowy silhouette.
That was M87.
M87, the supermassive black hole in a distant galaxy. They didn't image the black hole itself because it emits no light, but they imaged the superheated gas swirling around the event horizon, forming a bright ring. The shadow in the middle is where the black hole is capturing the light.
And it looked just like the theories predicted.
Astonishingly close to the predictions from Einstein's general relativity, a stunning visual confirmation.
And the other big breakthrough was gravitational waves.
Absolutely. The LIGO and Virgo detectors have detected the gravitational waves, these ripples in space-time itself, from dozens of merging black holes and also merging neutron stars.
So when two black holes spiral into each other and merge,
it's an incredibly violent event that radiates a huge amount of energy away as these space-time ripples, traveling across the universe at the speed of light. Detecting them lets us hear these cosmic collisions.
Hear the universe. That's incredible.
It's opened up a completely new way to observe the universe, confirming black holes exist, that they merge, and that space-time really does ripple, just as Einstein predicted.
Okay, but then there's this more speculative question the source mentions. But could black holes also be gateways to new universes?
Ah, yes, the sci-fi favorite. This is where things get highly theoretical and speculative, but it definitely stirs the imagination.
So is there any actual physics behind that idea?
Well, some theoretical frameworks explore possibilities. The concept of wormholes, for instance, hypothetical shortcuts through spacetime.
Tunnels through space.
Kind of. In some models, the entrance to a wormhole might look like a black hole from the outside. Whether stable, traversable wormholes could actually exist according to known physics is highly debatable, probably unlikely. But the idea is that the singularity might not be an endpoint, but a connection.
To where? Another part of our universe, or somewhere else entirely?
Potentially either. Some theories even link black holes to the birth of new baby universes within them, or speculate about cyclical universe models where black holes play a role in recycling matter for a new cosmic iteration after a big crunch.
So very much on the frontiers of theoretical physics.
Extremely speculative, zero observational evidence. But it shows how black holes push our understanding to the absolute limit, forcing us to consider these mind-bending possibilities when we think about extreme gravity and the nature of space-time itself.
Yeah, imagining that intense space-time warping around them, like a bowling ball on a rubber sheet, and those glowing hot accretion disks feeding them. It's dramatic stuff.
It really is. And if black holes represent the extreme of gravity-bending space-time, thinking about the quantum realm takes us to another level of weirdness entirely.
And that leap takes us to maybe the most out there concept yet, the multiverse.
Yeah, things definitely get weirder from here.
It really feels like the more we learn, the weirder the cosmos becomes. And this multiverse idea often starts with quantum mechanics, right? With things like quantum fluctuations in empty space give rise to particles popping in and out of existence.
That's a key part of it, yeah. The quantum realm is fundamentally bizarre. It doesn't operate by our familiar classical rules.
How so? What's the core weirdness?
It's governed by uncertainty and probability. Particles don't have definite properties like position or momentum until you measure them. And yes, even the vacuum of empty space isn't truly empty.
It's fizzing with activity.
Exactly. It's fizzing with these virtual particles, pairs of particles and antiparticles that borrow energy from the vacuum to pop into existence for incredibly short moments, then annihilate each other and disappear again.
They're not real particles we can capture.
Not directly, but their collective effects are real and measurable. They influence the properties of space and fundamental forces. It shows that reality at its base level is this constantly fluctuating probabilistic quantum foam.
Okay, so quantum foam. How does that lead to multiple universes? What's the connection?
Well, so what does this all mean for cosmology? Several different lines of thought in theoretical physics, building on quantum ideas, naturally seem to lead to multiverse scenarios.
It's not just one theory, then?
No. Several independent ideas point in a similar direction. One comes from inflation, the theory we discussed earlier.
How does inflation suggest other universes?
In many inflationary models, particularly one called eternal inflation, the inflationary process doesn't just happen once in our patch of space and then stop everywhere. Instead, inflation stops in some regions, forming bubble universes like ours. But it continues eternally in the space between these bubbles, constantly spawning new bubbles, new universes, potentially an infinite number of them.
Wow. Like a cosmic bubble bath that never stops?
Kind of, yeah. A fractal-like structure of eternally inflating space, spawning bubble universes.
Okay, what other ideas lead there?
Another comes from string theory, or more specifically M theory, which is an attempt to unify all forces and particles.
The theory of everything.
That's the goal. M theory postulates extraspatial dimensions beyond our familiar three. In this picture, our universe might be a three-dimensional brane, like a membrane floating in a higher dimensional space, called the bulk.
Okay.
And there could be other parallel branes floating in the bulk, each representing a separate universe. Sometimes these branes might even collide, potentially triggering events like a Big Bang.
So universes like giant sheets in a higher dimension.
That's one visualization, yes. And then there's an interpretation within quantum mechanics itself.
Called the many worlds interpretation.
Exactly. This tackles the weirdness of quantum measurement. It suggests that every time a quantum system could have multiple outcomes, like a particle being here or there, the universe actually splits into parallel branches, with each branch realizing one of the possible outcomes. So there's a universe where the particle is here, and another parallel universe where it's there. And this branching happens constantly with every quantum event.
So an unimaginably vast number of parallel realities constantly splitting off.
That's the premise. It avoids some philosophical problems in quantum theory, but at the cost of postulating this enormous proliferation of universes.
Mind blown. So the overall idea is, some theories propose that our universe is one of many a single bubble in a vast multiverse.
Each with its own laws of physics. And that part is maybe the most profound implication.
Different laws of physics, how could that work?
Well, in the eternal inflation or string theory scenarios, the way inflation ends or the way the extra dimensions curl up in string theory could be different in each bubble universe or on each brain. This could lead to different values for the fundamental constants of nature, like the strength of gravity, the speed of light, the masses of particles. Even the number of spatial dimensions could potentially vary.
So universe is totally alien to ours, where atoms couldn't form or stars couldn't ignite.
Precisely. Universes where the physics is just wrong for complexity or life as we know it to emerge.
Which makes our universe, with its just right physics,
potentially just one lucky outcome among a near-infinite ensemble. It offers an explanation for the apparent fine-tuning of our universe's constants. We simply live in one of the bubbles where the conditions happen to be right for us to exist and observe it.
It sidesteps the need for a tuner by just having countless possibilities.
That's the appeal for many physicists. If there are enough universes, one like ours is bound to happen eventually, statistically.
It really forces you to reconsider everything. If our universe is just one bubble, just one possibility realized out of countless others, what does that say about our uniqueness? Or the specialness we tend to feel?
It certainly challenges anthropocentric views, doesn't it? We might just be inhabitants of one somewhat typical, or maybe atypical, we don't know, universe among a vast cosmic landscape.
Yeah, it's like discovering your hometown isn't the only town, then your country isn't the only country, then your planet. It just keeps scaling up.
Exactly. It expands the scope of reality, potentially infinitely beyond our observable horizon.
And could there really be universes where fundamental things are different? Like gravity repelling, or time flowing backwards?
Theoretically, if the fundamental laws can vary, then yes, such bizarre universes might exist within the multiverse framework. We have no way to access or test them currently, of course. It remains highly speculative.
But the possibility, the single bubble in a vast multiverse concept, it really pushes us to imagine these completely alternate realities.
It does. It challenges our fundamental assumptions about what reality even is.
And it feels like as we ask these bigger and bigger questions, based on what we do know, we just uncover more profound mysteries.
That seems to be the pattern, doesn't it? For every answer, we find deeper, more perplexing questions.
So we've covered this incredible journey from the Big Bang and inflation, through dark matter and dark energy, black holes, even the multiverse.
Quite a trip.
Yeah, but as we've seen again and again, despite everything we have figured out, mysteries abound. The quest for understanding is definitely not over.
Far from it. In many ways, the more we learn, the more we realize how much we don't know. Like peeling an infinite onion.
So what are some of the biggest remaining questions? You mentioned the idea of what's beyond our cosmic horizon. What does that really mean?
Right. That comes down to the observable universe. Because light travels at a finite speed, and the universe has a finite age, about 13.8 billion years, there's a limit to how far we can see.
Light from further away hasn't had time to reach us yet.
Exactly. That defines our cosmic horizon, the boundary of the region of space whose light has had time to reach us since the Big Bang. It's currently about 46.5 billion light years away in every direction, accounting for the expansion of space.
So the universe is likely much bigger than that. We just can't see the rest.
Almost certainly much, much bigger. It could even be infinitely large. What lies beyond our horizon, more galaxies like ours, something completely different. We simply have no way of knowing directly. It's a fundamental limit.
A tantalizing unknown right there. And then probably the biggest question of all for many people. Are we alone?
Ah, the eternal question. It connects directly back to the vastness we've been discussing.
Yeah, you think about billions of galaxies, trillions of stars, probably quadrillions of planets.
Yeah.
It just feels statistically like life should have arisen elsewhere, maybe many times over.
The numbers certainly suggest it should be common. Yeah.
Yet we have no definitive evidence. The famous Fermi paradox. If alien life, even intelligent advanced life, is probable, then where is everybody?
It's a profound puzzle. Why the apparent silence? Are we genuinely alone, or is life common but civilizations rare or short-lived? Or are we just not looking in the right way? Or is interstellar travel simply too hard? Many possible solutions, but no answers yet.
And these kinds of questions, these huge unsolved problems, why do they grip us so much? Why do they motivate scientists and fascinate all of us?
I think it's because they touch the core of our existence, right? This raises an important question. Why care? Because it's about understanding ourselves, our origins, our place in this vast, incredible cosmos. It speaks to our innate curiosity.
The drive to know.
Exactly. The drive to explore, to understand reality. For scientists, it's the thrill of the chase, pushing boundaries. For everyone, it's the awe and wonder, the sheer scale and mystery of it all.
And then there's the ultimate fate question again, tied back to dark energy.
Right. Ultimate fate of everything.
Yeah.
Will it be the big freeze, the big rip, maybe a big crunch if dark energy behaves unexpectedly, or something else entirely, like a cyclical universe?
Our cosmic destiny is still TBD.
Very much so. It depends entirely on the properties of dark energy and dark matter, which we still don't fully understand.
So these huge questions are what drive future science, future missions.
Absolutely. They motivate the development of new theories and new technologies. Think about the James Webb Space Telescope. It's giving us views of the earliest galaxies, helping us understand cosmic dawn. Future gravitational wave detectors like LISA might poke the Big Bang or inflation itself. Missions searching for biosignatures on exoplanets are directly tackling the "are we alone" question.
So humanity's efforts, observing the sky with ever more powerful telescopes, launching ambitious space exploration missions, it's all part of chipping away at these mysteries.
It is. It's like assembling this giant cosmic puzzle. Every discovery, every observation adds another piece, sometimes changing our view of the whole picture.
Yeah, the cosmos is a puzzle, and every discovery is just the beginning, adding more pieces, making the picture bigger and more complex.
Right.
Hashtag, outro.
Wow, what a journey. We've really taken a deep dive today, haven't we? Through some of the most profound, mind-bending mysteries the universe has to offer.
We definitely covered a lot of ground.
From the Big Bang and that incredible inflationary burst right at the start, through the invisible dominance of dark matter and dark energy shaping everything, into the crazy extremes of black holes, and even pondering realities beyond our own with the multiverse idea.
It really underscores how much we've learned, but also how much remains unknown. Exactly. The cosmos really is this ongoing puzzle. And like we said, every discovery feels like just the beginning of understanding the next layer. We really hope that walking away from this deep dive, you feel, well, seriously well-informed. And hopefully you had a few of those aha moments, maybe sparking a renewed sense of just sheer wonder about it all.
That sense of wonder is key, I think.
It really is. It's what keeps us looking up, keeps us asking questions, and we definitely invite you to carry that feeling with you.
Absolutely. And, if we connect this to the bigger picture one last time, maybe the thing to ponder is just how interconnected it all is.
How so?
Think about the relationship between the tiniest scales, the quantum realm, those fluctuations we talked about, and the largest scales, the entire structure of the cosmos.
Right. The quantum seeds grew into galaxies.
Exactly. The physics of the incredibly small dictated the fate of the incredibly large. It's a powerful reminder that understanding the universe requires bridging these vastly different scales. It's all part of one reality.
That's a great point.
And maybe the journey isn't about finding all the answers. Maybe it's more about learning to ask better questions and just appreciating the sheer stunning scope of what's out there still waiting to be discovered. Our human desire to understand, even when faced with these almost infinite unknowns, that's pretty remarkable in itself.
It really is. A universe full of mysteries and us trying to figure it out.
So, yeah.
Yeah.
Keep looking up, keep asking questions.
Yeah.
And never stop wondering.